turn to
Okay,
my
so let
yeah.
me introduce you our speaker for today first. So good morning, good afternoon, good evening, everyone who joined us. My name is Chanan, and I'm part of this new initiative sponsored by the Royal Academy of Engineering in the UK, and we call this initiative July Next Energy. So we set to kind of to find the missing gap of the energy transition, especially for Thailand. But we learn from all over the world. We learn how other country is doing, and to do that, we organize workshops. And this is a webinar series. And today we have very special guest, Professor Sorin OLARU, from the University Paris-Saclay in
Yeah.
France. And he will talk about a really interesting topic and really important topic for energy transition. As we know, as we are moving toward the renewable energy, we create a lot of stress and strain on the traditional electrical grid, because the renewable energy is intermittent. You don't get the energy all the time, and the demand and supply and so on. So today we will hear how Professor is using the control system engineering to tackle this problem. Um, and yeah, so the format of today's talk will be the talk about 40 minutes to 50 minutes, and then some Q&A. So if you have any question, please feel free to leave your comments, or yeah, send your question over and then I can read it out. Yeah, so let's give the floor to Professor Sorin.
Thank you, thank you for the kind invitations. Thank you for being here just before the weekend. It's Friday afternoon in Thailand, early in the morning here. So I'm Sorin OLARU. I'm a professor in Paris, which is a school of engineering, which is part of the much larger university, Paris-Saclay, relatively young university, has 15 years and is a merger of four older universities and other research centers. And my affiliation is, as you can see, RT chair at Central Square. RT is the transmission system operator in France, and they are financing by now 10-year research, long-term research framework in our school, and I am the head of this chair. And I'll talk today about the use of predicting control for congestion management. And you'll see how the high power batteries are used as a lever for control in that framework. So, a few words about the complexity of the systems. We are talking about internet and other complex engineering system, but I like to recall that electrification is practically the greatest engineering achievement by the complexity of the grid, of the interconnection of the producers and consumers and their interoperability. So yeah, we are using a very complex system, and probably is the most emblematic example of system of systems. Now, let's focus. I come from Europe, so I will talk about the European case. There are 5 synchronous zones of operation in Europe. So the mainland, then you have the Scandinavian countries that are using their own synchronization zone. Then you have the former Soviet Baltic countries that, of course, historically have their own operation mode, and then Ireland and UK with their different zones due to the island type of geographical position. Now, for the proper operation and secure and optimal operation of those zones, there are 36 countries and 43 TSO, transmission system operators, that are there to secure the power system in real time, to perform the optimization at the economical level, and ensure that the asset, the hardware is working properly. Now, few figures in order to understand the consumption and the installed capacity and the population, which depends on the proper functioning of this system. And now, if we go even higher with the zoom in the European landscape, the French territory is one of the practically the one with the highest density of the grid and of the mesh of the grid. As well, you can see the figures in here, 105,000 kilometers of transmission lines. So we are talking here only about the high voltage lines, so above 60 kilovolt up to 400 kilovolt. Almost 3,000 substations, and of course, in order to control and have the real-time measurements, there are communication cables and interconnectors in there. I'm mentioning that because all this communication implies delay. And of course, the decisions are taken in the control centers. There are 8 around the country, and they are there to secure the functioning, and if ever there is a problem, to be sure that problem will remain local and will not propagate around the country. For example, now we are preparing for the Olympic Games, and one of these control centers will handle exclusively the Paris region and be sure that the power of all the installations is secure. And also another role of the TSO is to enable new market designs. This means that we are talking now about energy markets. So is there in order to be sure that those that want to develop solutions and to be able to connect to the grid to play in the open economy. Okay. What are the challenges in there? The system is there for maybe more than 50 years, is developing, but not very fast. However, there is a momentum on the generation based on renewable energy sources. Of course, due to the environmental attractiveness and that positive part of the renewables come from the operation of the network with important challenges, because these are not like the big inertial machines that we used to have from producing energy. They have a low controllability, and well, if we want to stop or to start such farms of wind producers or photovoltaic producers. Well, there are orders to be sent. There is communication, and that cannot be done at any level. Generally, it's on off, and sometimes some percentages that has to be done with a certain care. However, there are also economical aspects, and of course the stability of the power system that has to be. But I think, as we are not having anymore those inertial machines that have the advantage also of stabilizing and bringing. Avoiding the fast dynamics to be propagated. Well, now with the renewable energies, the power converters can bring some stability issues. So yesterday or 10 years ago, we were talking about physical layer and the cyber layer, where the communication and decision was taken. Well, currently, more and more on the lower level, we have the use of control systems, either for the power converters or for the decision making at the local zonal level, to be taken before transmitting the information at the centralized level. The centralized level being there practically only for day or week ahead decisions, strategical and not operational or safety decisions. Okay, so that was a long introduction. Let me go closer to the subject of my talk today. So we will be interested about what happens and what can go wrong on these big transmission lines. Well, a little bit of history on the left in here. It's a very simplistic representation of a zone as it has been designed like 50 years ago. You know, France is one of those countries with large nuclear power production. So the entire system was designed in a sort of centralized and pyramidal way with big production units, and then high voltage lines to dispatch the energy into the territory, and then substations, and then the distribution on lower and lower voltage levels. And in that design, the flows were very clearly indicated, so we knew what power flow will have on some line, and the design was done accordingly in order to ensure that the capacity allows the flow to be transferred in a secure way. And there was no big issue in there. Now, with the inclusion of renewables, for example, the green spots in here are some renewable energy farm that are installed. Well, the geography make that the position of those farms are cannot be chosen. They are imposed by the solar exposure or the wind optimal position. So you have to connect those producers at the closest point to their location. And when you connect them in there, maybe that connection point it's on a line which was not designed to have a huge flow. And you can see, I mean, here the direction was on, the flow was going on some direction as the producer, renewable producer here is connected. Well, the flow is reverted on this line, and that can be bring a large congestion. And even on the other lines, you can have a change of direction, and this means what I'm doing, this very simple representation, is to realize that all the studies that have been done at the design have to be updated according to the new operation mode. Why? Of course, because if there is a congestion in there, the line can melt, and then we are very close to the disaster with the danger of blackouts. Of course, well, what you can do to solve this problem is to build new lines. But new lines means new pillars, and obviously there is no municipality that wants to have new pillars in there, and it's ugly, it's difficult to maintain. So we would like to to have an update of the infrastructure as small as possible, but in the same time we have to have safety operations. So what RTE done is to construct in the very sensitive nodes a supplementary level of control, which is a storage unit. There are 3 currently installed in France, and there is a plan for 15 more. So these are very large storage units with batteries of 12 megawatt up to 24 megawatt, and to have a understanding of what that means practically, that correspond to a consumption of 10,000 households. So important capacity, and that comes with an important advantage from the control point of view. There is no delay in the operation and in the storage of energy within these units, so the flexibility is there. We increase the control degrees of freedom. The delays are relatively small, and there is, from the economical point of view, another aspect. Those batteries can be used for other services than the congestion management. You'll see at the end of my talk some figures in that respect. But first, safety. So we have to deal with the congestion management using the classical curtailment actions and these newly installed batteries. And well, there are 2 levels. One which is practically controlling at the pace of 5 seconds, and then a second level with the control at the order of 10 minutes, and then you have the forecast, the scheduling, the so-called scheduling at day ahead plans. So we will look at the very low part in here, at the zone of the grid, and we will see what's happening in there and what are the strategies that we put in place. So let's start gradually with the so you have the lines as the ones that you saw on the first picture. So the operation constraints say, well, the flow on this line has to stay below this permanent rating level. If ever, due to an incident or an injection from one of those renewable farms, pump in, and it happens that the power flow violates the permanent rating, then control actions, emergency control actions, have to be taken in such a way that if the overshoot is higher than a certain long-term rating, then the control action has to be aggressive in order to bring back the power flow in 1 minute below this level, and then in 5 minutes to bring it back to the permanent rating. Why? This is related to the heating equations. So if the power flow is higher than those limits, the temperature on the line increases, the line goes down, and well, if it's on a field, some cows can die, but if the line breaks, then the danger of blackout and cascade failure becomes apparent. Now, in order to take those decisions, and in order to bring down the power flows to their constraints, safety constraints, we'll use a model-based design strategy, which use the so-called power transmission and distribution factors. And from the control point of view, we'll use the model predictive control. So again, once we have this model, we'll use the model in order to make prediction on a finite window ahead, optimize the cost function, and satisfy the constraint, and then receive this optimization with the new measurements made available by the instrumentation. One change of the classical design framework for the predictive control. Again, predictive control is well established, is based on an optimization, and that optimization is generally a cost that involves some energy terms and energy of the control action. However, in the current case, this cost function, you have to see it as a very peculiar controller, as long as we are below the permanent rating, no control action should be taken. Why? If we send order of curtailment or storage of energy in the batteries, we are influencing the economical balance on the market, and RT is not there to influence the economical exchanges. So as long as we are below or within the constraints, no control action should be taken. We will have to take control actions only when we get to the limit of the feasibility, and that is a classical so-called viability problem. So in the predictive control framework, we will have to be careful and not introduce performance kind of criteria, because that come against the rules of the TSO. Okay, but before going to the cost function design, let's see what's the model. And in fact, the model that we'll use, you saw the sampling time, it's somewhere at 5 seconds. So we are not going very, very low as a sampling time, not very high neither, but from the congestion point of view, we can work with the DC approximation, and we'll start with very simple balance equation. So the sum of the flows on one node will be the difference of injections and subtractions of powers on the respective lines. So under lossless transmission, flat voltage profile, and small variation of phase, this model is valid. And the key point in here is to find those coefficients in here, which are called the PTDF, power transmission and distribution factors. What's the philosophy? For example, in order to find the coefficient relating an increase of 1 megawatt on this particular node N, we have to see how this increment will distribute along the lines. And there is a very simple offline study that can be done in order to see the propagation of this +1 with 0,9 +1, and then the 0,9 distributes along the grid. And in this way, for each increment on a node, will have a particular coefficient for the lines, even for those that are far from the place where the adjustment of the production of the subtraction takes place. So there is a work to be done offline in order to construct those power transmission distributed factors. And once they are available, well, we can use that as a local model, for example, for a particular zone that has been identified as to be congested. And I will carry on this example in here with, I don't know, 6 nodes, and then interconnection with some neighbor regions that are depicted in red here. So if I try to bring the model into a sort of state space representation, so the main dynamic will be an integrator-like dynamic for the flows passing by these PDDFs, and the levels for the control are the injection on the batteries, the energy that I can store, that's practically instantaneous, and then curtailment orders to the renewable energy producers. As you can see in here, this comes with a delay, and generally for the wind farms and the solar plant that we deal with, this is 45 seconds, so about 1 minute delay from the moment when the decision is taken up to its acknowledgement and enforcement at the production side. Then, of course, for the battery we saw before, there are bounds on the energy. We have also, yeah, the instantaneous increment cannot be cannot overpass some ranges, so we have to store that in a state variable, and in a compact form, practically in a rough approximation, you can see this as a linear system effective by time delays and, of course, of constraints. The constraints are those coming from the rating on the lines, from the power and energy of the batteries, and of the level of curtailment that we can apply for the producers. Now, as you can see, those constraints can be written in they are linear, so they can be written in a linear form. So again, that's probably one of the easiest formulation of a cost function for the formulation of the predictive controller, with cost function in here. Now, again, recall, we don't have a trajectory. That's the classical way of defining a predictive controller, and here is the reference. But again, there is no reference for the flow. There is no reference flow on a line. The flow has to be left free of evolution and has to be constrained only when it comes to the boundary of the feasible region. Now, however, I put here in the slide XREF because for the battery, what we can have is to have a reference level, which is, for example, the battery to be discharged in order to be able to face new congestion events. So after a congestion, it will be smart and good for the long term to bring back the battery to an empty level in order to have freedom, degrees of freedom for control later on. And of course, the second term only says that we like to curtail to impact the natural functioning of the transmission as low as possible. So, in a nutshell, that's the optimization problem. Very simple quadratic formulation in here. However, recall that there is a delay on the control channel, so the prediction horizon has to go above this control. And generally, when there is delay and constraint playing on the state variables, you may run into feasibility problems. However, you should recall that that feasibility can only appear during the time the time window of length of the delay, because as soon as the delay passed, the control action will be there, and we can shut down everything. We can shut down all the renewables, all the production units, and we can bring back the flows to the bounds. Now, that's the result of the predictive control operating on a zone which has one battery here. You see this node in here has a generator and a battery. And let me spend a few minutes on this slide. So what you have in here is the production profile on one of the, I think it's on the node 10,000. So what you have to see is the black curve. That's the production, and if that will follow its trend, then you'll have on the lines, three of represented here, three of the lines in the zone. You'll have a growth of the power flow on the line, and yeah, that's the no, sorry, I made a mistake. That's the other way around. The three graphics up there are the production profiles on three of the nodes. So the black curve is the production going up with different profile. Practically is the same profile but shifted with a time delay. You have to see that, for example, on the wind farm. When the wind increases, there will be a first farm which benefits, so there will be an increase of power for that farm, and then the wind wave, yeah, those travels, and you have another farm which benefits, and so on and so forth. Now, when those generation units increase their production, the flow increases, and that's the line power flow depicted in a lower left graphic, and the dotted line shows that the limit of 45 megawatt is overpassed around 400 seconds. So if no control is done in terms of curtailment or battery storage, you run into a blackout type of emergency situation due to the loss of a transmission line. So, as you can see somewhere in here at time 400, the MPC is looking at the predictions and makes a smart decision. I mean, on those three units in there, it sends. So first of all, around 400, it starts filling in the battery with a very aggressive maneuver. However, the trend is relatively aggressive at the beginning. You see it goes up with a relatively steep increase. So what's happening here? You see that in red there is a curtailment order that it sent in order to safeguard the future functioning. So at this level in here, there is a curtailment order which cuts practically the production of this farm and which is not following anymore the available production, but a lower level. And after this order of curtailment, obviously, as the trend is not followed with another increase on the lines, the control algorithm is discharging the battery. You see, it comes to zero and is ready for a new congestion event. And the congestion event appears, you see, is the third unit that goes up. And well, this increase is able to be handled by the battery. So there is no curtailment order, supplementary curtailment order sent from 500 to 900 seconds. However, then there is another increase in the production curves. And what you see in here is that the curtailment order that has been sent previously for this line becomes active. So does it mean that if a curtailment order has been sent, that is really activated? It will be activated at the moment when the production overpassed that percentage of the installed production. Bottom line, if you look at this graph in here, we are staying within the bounds, of course, with some variations. Why are those variations in here and we are not staying clearly at 45? Is because you have interconnection with the neighboring regions. So we are controlling what's happening in these regions, but we are affected by the flows that perturb the functioning within our zones. Okay, I don't know how I am with the time. Okay, I'll try to speed up because what is next? There are variations around this idea. So what we noticed is that as we are taking into account the worst trend with respect to the production, we can be sometimes very conservative and start sending curtailment orders as soon as the battery is full and the trend of production is aggressive. So in order to handle that, we went into a scenario-based MPC instead of taking the worst realization of the disturbances. Now I'll call disturbances the unknown production within generation within my zone. So in order to handle that, we add a supplementary state variable, which is the power generated power, which is the previous generated power, plus the increase in the production and minus the curtailed action send tau yeah, there is a difference here in between the delay on the control order for the battery and the one for the production for the curtailment. Now, adding that, it allows us to take into account practically several scenarios for the generation in here. So yeah, again, in a compact representation, we have a linear model, but I made this term of additive disturbance appear explicitly. So yeah, what's happening is that with the production inside our zone, we can make different predictions according to the historical data that we have within the region. So the hard constraint remain the same. However, we can soften the constraint on the power flow on the line and use a variable limit which takes into account some probability according to the scenarios to be evaluated. And I will make an assumptions that we have at least NS number of scenarios in there, and each of these scenarios come with a certain probability. In some, those probability will be equal 1. And now I will briefly show you how those elements enter into the MPC design. So practically, yeah, those relaxation variables epsilon. Well, for J, we'll go for we'll span all the scenarios. So for each scenario and for each moment in the prediction horizon, we have to allow only, I don't know, for example, 1% of violation. Then if you sum all the violation, all the activation of those softening constraints along the scenarios and the prediction horizon, you don't have to have more than yeah, of course it's normalized here. So, but again, you can put a ratio, a percentage in there, and and then, but those will be like absolute values, and then there is the stochastic part. So according to the probabilities of each of those scenarios, you see the P is related to each of the scenarios. Then I can play with the importance of the respective scenarios in the activation of the softening constraint. You have to, I have to stress that for tau is the delay time for the control. So I will not consider softening constraints after the time moment when the control action can mitigate the congestion. So those are there only to handle the violation, while the curtailment cannot handle the congestion. So with these elements, well, the MPC starts being a little bit more complex, but not complex from the structure, because all the things that you see in here can be casted as a large linear programming or quadratic programming if you consider quadratic cost in here. So we are in the same scenario as before, again, for generators. And if you look at the behavior in black, you have practically the previous algorithm. No, in red is the reference strategy, the MPC. So you see the curtailment have been, orders have been sent earlier in time. Well, with this probabilistic and scenario-based approach, we curtail less energy and we delay a little bit the curtailment order. So again, the nominal MPC, the robust MPC, the one which takes the worst trend into account, activates the curtailment earlier, and we managed to prove that by allowing this setback of the constraints, we stay, we win practically 11% of renewable energy that is still produced and not curtailed. You may wonder, okay, is any, well, how this is handled? Well, it is handled mainly by the storage in the batteries as the increment of storage. And you see, after handling an event, there is also the discharge of the battery in order to stay around zero in here. And you may wonder, okay, there is any safety price to be paid? And the good news is that practically no. You see in red here is what the nominal MPC would do, and the scenario-based MPC is doing practically with the same performance in terms of safety. And you see here we go even, we shave practically the constraint limit. Now I think I am 43. I'll do it very fast if I'm allowed, 5 minutes, and I'll finish. So now,
please go ahead.
Okay, thank you. So in what you saw till now, the curtailment orders, let me get back here, the curtailment orders are monotonic curves. When you start curtailing, will not revert that control action. So it will go along like that, and then the information about a curtailment signal is sent to the central control unit room, and in there, once the congestion is mitigated, those curtailment orders are reverted practically manually at some moment in a day. And there is a huge loss from the renewable generation point of view. And what we show recently in a European Control Conference less than 6 months ago, is that practically the MPC can handle also the relaxation of curtailment orders. Now, I take back I go back to so that's the model that you saw before. Now, if you want to go closer to the mechanism of the generation, so yeah, you have here, that's the rated generation capacity for one node. Well, it will produce the maximum, the installed power minus what you curtailed, and of course that's a dynamical process, minus the curtailment orders that you sent tau instance before. However, those are like wish lists, so we would like to produce that. The real produced power is practically the power available according to the wind, for example, and the increment in that production according to the current meteorological conditions. So there is a minimum in between those signals in here. So if you want to go to have a precise model, you have to, the update of the generated power has to have this switch in between two signals, and that increases a little bit the complexity of the prediction mechanism. And more than that, when you are willing to relax a former curtailment order, you have to be careful, because the currently power available can go and intersect the curtailment curve, and once this behavior appears, practically you enter into a blind spot, because you don't know exactly what will be the available power once the available power is higher than the installed minus curtailed level of production. So in order to mitigate this lack of information, took very simple approach. So as long as, so if the current power available is already higher than generation minus the maximal generation minus the curtail, we are already in the blind spot. So if I want to relax the curtailment, I will simply consider the worst case, meaning that along the prediction horizon, I will consider that the available power is at the maximum. If on the contrary, I was below the curtail level, but the trend is going above, what I will do, I will consider that the available power is following that trend, but from the moment when the curve meets the curtailment power. So practically, I'll consider that the available power grows with this upper bound in here. So with these two cases that you can code with very simple mixed integer type of variables, you can perform again a prediction of a long horizon with that's the part where only the battery is available, and then both curtailment and battery can be used. And well, the dynamical equations are the same, but there is this disjunctive inequalities that take have to be considered. The costs stay the same, and with the same scenario as before, you can see here. So again, we have on the upper part, you have the production units, though they go higher and higher. And what is interesting to see here, the blue curve in here is the curtailment order, and it's not anymore a monotonic curve. Here, the algorithm, the control algorithm, sees that there is a potential problem. It sends a curtailment order, but as the trend is not followed with a positive production, well, it releases the curtailment in here, at least for this producer. It keeps the curtailment for the second one. I mean, it sends a quite violent curtailment order, then it relaxes it, and then finds practically an optimal value of curtailment. And yeah, interestingly here, for the third one, it sends curtailment orders that are not really activated because the curtailment curve doesn't meet the production curve, and then it stays above the production, and only later on deals with the congestion on the last part. And again, I mean, you can see the performance in terms of we are well below the limits, and the battery it's used practically all the time to handle the congestion. Yeah, bottom line, so we had a nominal MPC which is currently implemented in the on the field. We propose a new scenario-based MPC, which is very is performant in the sense that it can exploit the historical data and relax a little bit the worst case scenario. We are currently showing that working on to show that the PTDF don't need to be computed offline and can be really estimated in real time, and that will make a time varying MPC formulation. And yeah, in order to give you now, once that we have those control algorithms, we can also do analysis on long term, like for a year around. And this is probably the most interesting message to take home. So with these batteries that are installed in there, in the summertime, the congestions are practically 3% of the usage. They are partially used on 6% of the time, and the 94% of the time the battery is fully available for other services. In winter, those percentages go a little bit higher, but there are still 85% of the time available for doing other services like energy storage. You can have a energy stock market, and those batteries can be used in that sense. Here there are some references, a list of collaborators, and as I was discussing with your colleague in June, we are organizing one of the most prestigious power system computation event. So you are welcome to join us in France for this event, which is just before the Olympics. So if you are interested in sports and the Olympic games, you can continue your summer in France. Thank you, and I'm open for questions and discussions.
Sorry. Can you hear me?
Yes. Yeah. Now.
All right, so it's time for Q&A. If anyone from the audience has any questions, please feel free to write it down. Otherwise, I will start with a really simple question. So in your point of view, like you heard about the renewable energy mix. So basically we want to, for example, in Thailand, we want to increase the renewable energy mix into the grid. And right now it's about 20%, but in some countries it's already at 30%, but I'm not sure how far we can go because of this problem. So in your proposed solution with the battery, do you think with the right control and management system, like how many percent, if you have to think about the context of Thailand where we have solar and wind, how many percent can we go?
So there are 2 points in here. So the depends on, I'm not aware about the infrastructure from the transmission lines. In what may concern the transmission lines, the batteries are there. I mean, nobody wants to redesign the infrastructure. So that's a very complicated problem. So for that's one of the hard constraints for the injection of renewables. It can be handled, as I discussed here, by handling only the congestion point-wise. But there is, of course, the other more flexible alternative is to add the storage at the production site, and then be able to to inject in the grid only when it is needed, and to be able to to adjust according to the to the forecast. But that's another problem, because the producers are not the operators of the centralized level. So okay, to answer your question, you have to be aware also that the renewable injection will come with a issue on the stability side. So it will be good to maintain the classical inertial machines in there in order to have a sort of robustness of the system. Otherwise, you have to be able to securely operate these injections with all the problems that they bring.
Let me put it another way. Like, in order for us to reach the net zero by 2065, 2050, do you think the traditional grid system can still remain intact, or we have to create completely new decentralized grid system for us?
I think the only solution, the only place that I am aware that can fix this target is Australia. Why? Because they have huge solar production, and anyway, the infrastructure, the grid, is so undeveloped that anyway they are about to build what the necessary infrastructure, very low interconnection. So you have to design it in a decentralized manner. But I mean, in the same time, there are good parts and difficulties in there. I don't see this okay, we can target the zero net, but by doing it locally, and we keep the historical grid for safety and for industrial necessities. I see there is a question. Thanks for the very informative presentation. Thank you. According to my understanding, FC worked really well with specific setup or task. My question is, does this method or framework able to apply that electrical control plant or in other countries, like to use it in a universal? It's exactly my message. Yes, I think the MPC, as it is designed as a framework for the control design for the congestion, at least, is universal. Now, what you need in order to use it is are those PTDF. You need a model. So the model, as I was saying, well, you have to build it by doing a study on your topology, and you have to have a simulator practically of your network beforehand. Now, that's undergoing work, and I will present that in April in a conference. What we showed that a simple receding horizon regression can allow building those coefficients in real time. Of course, you have to have excitation on the system. That's a classical control problem. If the curves are flat, if everybody is producing very on very flat curves, you'll not be able to know what will be the distribution of an increment on the lines. But if you operate with some very rough approximation, then you can adapt them in real time and learn those coefficients according to the modern learning strategies, and have very performant estimation. So practically that will be a learning-based MPC. So again, the answer is yes. This is a generic control design, and it can be adapted to any country, to any grid, to any topology. There is no major difficulty other than constructing this model. And this model can be, if you don't have simulators like RT has, which go very deep on the granularity, you can simply use learning technique, modern techniques, and obtain.
All right, I guess we have come to the finish. And on behalf of the organizing committee of JuฬาNext Energy, on behalf of Professor Surathep and Professor Anongnath, I would like to thank you again for spending your valuable time in the morning, the coffee time with us, and give us a really wonderful work understanding of what you have been doing. And this recording will be published on our website, and if you find it useful or helpful, you can always come back to this lecture. Once again, thank you very much. And
thank you for your time.
bye-bye.
Sorry for being a little bit long, and it's always a pleasure to discuss and collaborate with the colleagues from Chulalongkorn University. All my greetings to the colleagues. Okay, thank you.
Bye-bye.
Bye-bye. ขอบคุณครับ
ขอบคุณครับ